Welcome everybody to part 4 of this YMFC 3D video session. Now in this video I'll explain how to control the ESCs of the multicopter with an Arduino Uno. And as already explained in part 2, ESCs are controlled with a 1000 to 2000 microsecond pulse. And that the refresh rate of the ESC pulse of a multicopter controller is 250 Hz. Now let's look at the main program steps of the flight controller. The receiver inputs are collected via a interrupt subroutine, as described in part 2. This will run in the background so we don't have to worry about it. Now the main loop of the program involves various steps. Now the main steps are: read the gyro angular rate data, calculate the PID corrections, calculate the pulse for every ESC, compensate every pulse for voltage drop, and send the calculated pulses to the ESCs. Now here you see the I2C data transfer between the Arduino and the gyro. Now the scope is set for 50 microseconds per division. The total time it takes to transfer the data is approximately 300 microseconds. Now this pulse represents the calculation time for all the calculations that is needed to get the multicopter to fly. Before the calculations, a digital output is set to high. After the calculations, the output is set to low. Now this creates a pulse that is shown on the scope. And as you can see, the calculation takes approximately 600 microseconds. Now a program loop at 250 Hz gives us 4000 microseconds of available time. Reading the gyro angular rate data takes 300 microseconds. The calculations takes 600 microseconds. And when we subtract these times, we get 3100 microseconds of available time. Now the maximum pulse length for the ESCs is 2000 microseconds. So there is plenty of time to create the pulse for the ESCs after the calculations. Before using the digital pins as outputs, they need to be declared as outputs. Now normally this is done with the command pin mode. But there is a more efficient way to do this. Now this line sets bits in the data direction register of port B. Now the result is exactly the same as these two pin mode lines. More information about the DDRB register can be found in the manual of the ATmega 328. Now as you can see, the initial value of the register bits is 0. This means that all the ports are set to input by default. By setting the DDB4 and DDB5 bit, the corresponding ports are defined as outputs. Now in this pinout diagram, we see that the B4 and B5 ports correspond with the digital outputs 12 and 13 of the Arduino Uno. The Arduino software is made user-friendly. Now this however comes at a cost. After compiling the code, the size is 942 bytes. When compiling the code with the pin mode commands, the size is 1078 bytes. Now this is caused by the extra lines that creates the pin mode commands. Now let's upload the program and see what it does. Now you might think that setting the port high and low produces a very short pulse. Now unfortunately this is not the case. The overhead or extra code lines that come with the digital write command uses an enormous amount of clock cycles. Now I set the scope for 1 microsecond per division, and as you can see, the pulse is 4 microseconds long. By directly manipulating the port's register, the extra lines of the digital write command are ruled out. Now, as described in the manual of the ATmega 328, we can directly access the port B register and set the port B4 and port B5 bit. This will change the output state of the digital pins 12 and 13 of the Arduino Uno. We already know that the digital write command uses 942 bytes. When we compile the code with the port B manipulation line, the size is further reduced to 680 bytes. So with a few simple steps we reduce the size of the sketch tremendously. Now let's upload the code and have a look at the scope. Now as you can see, the length of the pulse is reduced from 4 microseconds to 200 nanoseconds. Now I think this makes a pretty big difference. Another thing worth mentioning is the time it takes to read the microsecond value. I use this line as an example. As already shown, the pulse takes 200 nanoseconds without extra program lines. Now the extra pulse length is created by reading the microsecond timer. Now let's upload. And this is not what you expect. The scope is set for 500 nanoseconds per division, making it a whopping 3.5 microseconds. Now this is something to keep in mind whenever you read the microsecond timer. This is the receiver input program that I used in part 2. Now I made some small changes to the interrupt routine to optimize the performance. The main change is the single microscale instead of the several microscale as before. This delay simulates the calculations and data transfer. We set output 12 to high and use the most logical command to create a pulse, delay microseconds. I will upload the code and show the results on the scope. And here we see our 1500 microsecond pulse. Now when I zoom in on the falling edge of the pulse, we see that there is a small jitter. Now this is caused by the interrupt routine of timer 0. Now timer 0 updates the microsecond clock. Now in this example, I disable timer 0 with this line, so there is no interrupt subroutine running on the background. Because the delay function does not work with timer 0, I use the delay microseconds instead. And after upload, we see a jitter-free falling edge of a perfect 1500 microsecond pulse. Okay, now back to the working timer 0 and the inevitable jitter. Now when I turn on the transmitter, the receiver signals become active. Now the pin change interrupt routine is only making things worse. Now 60 microseconds of jitter is not a very good base to start on. Another way of creating a pulse is via a hardware timer of the Amiga 328. A hardware timer creates an interrupt whenever a certain value is reached. Now these lines set up hardware timer 2 to create an interrupt every 4 microseconds. With every 16 MHz clock pulse, it counts from 0 to 63. When reaching 63, this interrupt subroutine is executed. Now in this subroutine, a counter is incremented. When it reaches 625, output 12 is set high. 1500 microseconds later, the timer reached 1000. Now the output is set low and the timer is reset. Now I don't go into the details because I just want to show you the results on the scope. Now here you see the falling edge when two interrupt subroutines, timer 0 and timer 2, are active. By activating the receiver interrupt subroutines also becomes active. Now there are 3 interrupt subroutines running. And as you can see, this is too much for the relatively slow Amiga 328, giving us a 30 microsecond jitter. Now to keep things as simple as possible, I found that the best way to create a pulse is by using the microsecond timer. In this example, the variable is loaded with the microsecond time increased with 1500 microseconds. The output is set high, and this while loop waits until the time is expired. And when it does, the output is set low. Despite the time it takes to read the microsecond function, the nasty microsecond correction and the interrupt routines that run in the background, we get a pretty decent pulse. Now the maximum jitter is approximately 20 microseconds and will do the job for our flight controller. Now this is the final program that I wrote for this video. I'll put a link in the description. The most parts are already discussed. This new part, however, is to make sure that the receiver signals are active and that the throttle is in the lowest position. If this is not the case, the main program will not start for safety reasons. To prevent the ESCs from beeping annoyingly, they are fed with a 1000 microsecond pulse at 250 Hz. And for the visualization, the LED state is changed every 500 milliseconds. Because the ESC pulses can vary in length, I implemented this loop timer to make sure that the refresh rate is always 250 Hz. The timer simply waits until the 4000 microseconds are expired. And after that, the loop timer is reset. Now this line sets the ESC output high, and the delay time is calculated in these lines. In this case, they're gonna be the same as the throttle input of the receiver. This while loop is executed until the 4 highest bits in the port D data register are 0. This equals the finishing of all the ESC pulses. Inside the loop, the delay times are checked. When the delay time expires, the corresponding port is set low. When all the ports are low, the while loop is terminated. Now I've uploaded the program to the quad and removed the props for safety. Turn the power on and we'll see that the red LED is flashing. Now it keeps flashing until the throttle stick is in the lowest position. After that, it is possible to control the motors with the throttle stick. If you set up the transmitter as described in part 2 of this video session, you have a 1000 to 2000 microsecond output pulse, making this program ideal for programming the ESCs when needed. And that brings us to the end of this video. If you have any questions, leave them in the comments below and subscribe so you don't miss the next video where I discuss the PID controller. I thank you for watching and see you next time.